To summarize what we did in the previous presentation, we were talking about a very complex electrical engineering system, a system that may be strung out across several components, very complex, perhaps, system. But we find that energy flows from one end of the system to the other. And this could be a transmitter where ultimately we have a source on one end and energy is flowing down to the transmit antenna. Or it could be a receiver, for example, where we have a receive antenna at one end, energy flows from the receive antenna down to the end of the receiver. Or it could be any electrical engineering system where that's connected together, and in those cases the energy is moving from in one direction toward the other. So we define or pick an arbitrary point on that system, and we define a point plane. And then everything point plane, everything to the left of the point plane, we put it inside a box. And this could be a lot of very sophisticated and impressive electrical engineering. But we're going to take that box, those elements inside of it, and we replace it with an equivalent. Since energy is flowing from that blue box, it is a source of energy, and we can replace it with an equivalent circuit that is either the Thevenin's or Norton's equivalent. Now, typically we use the Thevenin's, but again, no offense to Norton's, we could use Norton's just as effectively in the analysis. Everything then to the right of that port plane, where the energy is flowing toward, then everything in that blue box we define as the load. And we can go through, if those devices are linear and time invariant, we can replace them with an equivalent circuit, which is simply an impedance. It's input impedance. And that characterizes everything that we need to know about that blue box, regardless of how complex and how many elements might be inside. We really just need to know its input impedance. And so we replace this very complex and impressive set of electrical engineering with a almost trivial circuit. Simply a Thevenin's equivalent to source with the source impedance connected to an input impedance, which in this case we call the load with respect to the source. So we have a source impedance ZG and a load impedance ZL. Again, this is not physically what's happening here. These gray boxes that I put behind here try to remind you that, oh yeah, this is really a representation now of a more complex circuit inside of this box. We used to have the blue box and we replaced it with the circuit there. It's not like we look inside the box and what we see is just single lumped element of an impedance sitting there. We don't look inside this blue box to the left and see, oh, it's just a voltage source in series with the lumped element source. These are not physical representations of what is inside the box. The physical representations typically are very complex. No, these are simply equivalent representations of what's in the box. So we're going to pretend that that is what is inside, and that is sufficient if we want to determine what is going on right at this port plane. Specifically, what is the voltage at the port plane, and what is the current then at that port plane? From that, of course, we can determine then the rate at which energy is flowing across the port plane from left to right. The energy flow, the power. The power across that plane we define as either the power delivered from the source or the power absorbed by the load. In this case, of course, they're equal to each other by conservation of energy. If 32 millijoules per second flow out of the source, then 32 millijoules per second are being absorbed then by this load. From this equivalent circuit, we could determine the amount of power. Again, by conservation of energy, they're the same. And by simply KVL and Ohm's law, we came up with this result. Do we know this result is true? Well, there's some things we can look at and do a sanity check. And I always emphasize to students, do a sanity check on your algebra. Make sure that it looks physically correct. Have even had grad students sometimes will hand me a result and I'll look at it for a second and go, this isn't right. And they're very upset and sort of defensive and say, no, I spent hours working on this and I checked my math, multiple times and I'm sure it's correct. How can you just look at it immediately and say that it's wrong? Well, there's some sanity checks that you can do to make sure that at least it is a plausible answer. We can do that here. For example, power is a real value, and so the result we get must be a real value. And of course, this is problematic because the currents and voltages that we talk about, and in addition, the impedances are all complex value, yet the result for power must be real. And so check it out and make sure that it is. Notice we have magnitude squared of VG. Magnitude is a real value. We have the magnitude of the sum of these two impedances. The two impedances are complex, but if we take their magnitude, the magnitude of a complex number is a real value. Finally, we have RL. RL is simply the real part of ZL. And because we take the real part of ZL, it is a real number as well. And so this result is real, so that makes us feel better. The second part of the sanity check we do is, does it have the right dimensionality? In other words, does it have units of power? We go through the math and we look closely here, and we see that we get basically voltage squared divided by impedance in ohms, or we can look at that as volt current. And so this clearly does have the correct units for power. It's real valued, and it has units of power. We're doing well here. We've passed two of the sanity checks. There's one third sanity check that's important to look at in these cases. When we look at these results, we find this result, in fact, is dependent on each and every element of the equivalent circuit. When we look in here, basically there are three parameters, VG, ZG, and ZL, and those three parameters show up in our result for power. If we have a situation where we do an analysis of a circuit and the result only depends on some of the parameters or even one or two of the parameters, it's suspicious. It doesn't mean it can't happen, and we'll have a couple examples where the result is only dependent on a subset of the parameters of the circuit, but generally speaking, when we do analysis, it will depend on everything. The current and voltage that we get with respect to this circuit depends on any of these parameters, all of these parameters. We change one, we're going to change the current and voltage and thus the power, and the mathematics, the equation that result bears this out. So three sanity checks we did. It's a real value as it should be, it has the right units of power as it should have, and it involves all of the elements of the circuit, which is typically always the case. And so we feel comfortable about this result going forward. So let's look at this result more closely. Now, in most electrical engineering circuits, if we talk about the rate of energy flow, power, we want to make that energy flow as large as possible. Ultimately, the energy comes down to the end where we detect it, we demodulate, we recover the information. And what we'll find is the accuracy of that recovery is dependent on the power of that signal. Specifically, the power of the signal compared to the noise, the interference that causes error in our demodulation. So we want to make sure that we have an efficient transfer of power from one side of our circuit to the next. Specifically, in this example we have then, we want to make sure that the power absorbed by that load is as large as it possibly could be. And so we ask ourselves, how do we make sure that the rate of energy flow is maximized? Well, this is one of the most fundamental questions in electrical engineering, and it has one of the best known answers. However, it is also frequently misunderstood and misapplied and causes many battles and arguments among electrical engineers. The source of that argument, of that misunderstanding, is not a factual one in terms of what is the right or wrong answer. The source ultimately is the ambiguity of how the question is asked. We talk about how do we maximize power transfer. Well, that's far too ambiguous and unclear to be able to answer. What do we mean by how do we maximize? What do you mean by what are we trying to change? What are our fixed parameters? What are our free parameters? And what ultimately are we trying to optimize? Those are the three things that we need to know for any question of optimization. Fixed, variables, optimization, parameter. If we do that unambiguously, then the answer will be clear, and what we'll find is we get different answers depending on how we ask that question. And that, of course, is the source of the controversy. The answer depends on the question that you ask, and you have to be clear in how you ask it. So here's the first question that we're going to ask. And again, we're going to try to ask it very carefully and unambiguously so that we know our result cannot be disputed. If we go back and look at our equivalent circuit and equivalent source for all the complex electrical engineering system to the left that's supplying energy at a certain rate, and a load impedance, which is the input impedance of equivalent circuit for some sophisticated piece of electrical engineering that's absorbing energy to the right. If we look at this equivalent circuit, we're going to go through and first say what is fixed. And the thing that is fixed is our source. The source is the given. We have some value VG and ZG. We can't change it. We can't alter it. It's not a variable in this question, question that we're asking. So given a specific source, the question we're asking is, what should the value of the load be? The load is our variable. We can change the load. We're saying what load can we attach to this source in order for the power delivered to the source to be maximized. Given a source, what should we connect to it to maximize the delivered power? Now, by conservation of energy, maximize the delivered power, of course, maximizes the absorbed power since they are the same. So we could recast the question as saying what value of ZL will maximize the power absorbed by ZL given a specific source. If we go through and do the math to determine that, we can go through and do some differential optimization for complex numbers, and there are many textbooks that go through this procedure. What we find is a result that's fairly famous in electrical engineering. I'm sure you've seen it before. It turns out what we want to do is set this load impedance here, ZL, the input impedance of this box. We'd like to set it to be equal to the complex conjugate of the source impedance. If we set the load impedance to be equal to the complex conjugate of the source impedance, what we'll find is that the rate of energy flow out of that source is as high as it possibly can be. There is no other value of ZL that we can set or attach to the source and extract energy at a faster rate. This is the optimal solution for this specific question. A very important question that follows from this is, what is the rate of energy flow for the case where we have attached a load that is equal to the complex conjugate of the source impedance? We say that is the maximum rate at which the source can deliver energy. Well, what is that rate for that optimal case? It's fairly easy to determine. We simply go through and insert the value ZL is equal to the complex conjugate of ZG into our expression for the delivered power. And when we do that, we find it simplifies down to this result. And this result is very important. Many engineers, electrical engineers, know this complex conjugate rule. The load impedance should be the complex conjugate of the source. But the real important ramification of that is this idea of available power. When we extract the energy from the source at its maximum possible rate, it turns out to be this value. This value we call the available power of the source. Notice it depends on VG, a source parameter, and RG, the real part of the source impedance. In other words, this is a source parameter. It is independent of the load connected to it. This is not the power that the source delivers. This is the maximum power that the source delivers. That's what we call available power. I have this power available. Now, whether I really deliver to the load or not depends on the value of that load. A source parameter. If I have a source sitting in my desk drawer or sitting on the lab table, it has a specific available power, and there's nothing we can really do to alter it, say open up the source and try to change the circuit that is inside. So the available power is a parameter of the source only, a very important parameter or fact to make sure that you understand or remember, and it has this value. Again, something that depends only on the parameters of the equivalent source, Thevenin's equivalent. So an important fact to really bear in mind here, and this is a confusion for students, is the available power of the source is a source parameter. But the available power is not the value of power delivered by the source. The power delivered by a source is always going to be less than or equal to the available. Available is the maximum. Let's say we go through and we connect a load to our source, which is purely reactive. All right, a purely reactive load. How much, at what rate of energy can that purely reactive, or what rate can that purely reactive load absorb energy? I'm sorry. Well, if it's purely reactive, if it's inductor, capacitor, some combination, it can't absorb energy at all. The rate of energy flow is equal to zero. The power absorbed by a reactive element is equal to zero. Yet by conservation of energy, we know the power absorbed, in this case zero, must be equal to the power delivered by the source. So if we connect a reactive load to a source, the delivered power will be equal to zero. Of course, that's going to be far less than the available power. The power delivered by any source, therefore, has a minimum of zero, if a reactive load is connected to it, and a maximum that is equal to the available power. And that happens when the load is equal to the complex conjugate of this source. Generally speaking, the delivered power of the source will be somewhere between zero and the available power. To know exactly what it is, we need to know the load value that is attached to that source. Again, the delivered power of the source is equal to the available power if and only if, only in the special case where this load impedance is equal to the complex conjugate of that source. Now, you may be rolling your eyes a little bit and thinking, I know all this, you're really kind of beating a dead horse here. This is a fundamental rule of electrical engineering, this conjugate match and maximum power transfer and such. But let's go through and look at a different question. Again, to ask this question unambiguously, we need to define specifically what is fixed, specifically what is the variable, what can we change, and specifically what are we trying to optimize by changing that variable. In this case, we're going to do something slightly different than what we did before. In this case, we're going to make the load value fixed, given some load. ZL is what it is. We can't do anything about it. We're going to attach a source to that load, and we're going to ask ourselves, what value of ZG should we select? That becomes our variable, the source impedance ZG, such that the power absorbed by this load is maximized. Given ZL, what should ZG be to maximize the rate at which energy is absorbed by the load? Once again, by conservation of energy, the rate of energy that maximizes the rate of energy absorbed by the load is also the rate of energy that is delivered by the source. So we could also say, what should the value of ZG be that maximizes the rate of power or the rate of energy delivered by the source? At any rate, if I were to go through and ask this to electrical engineers, what we'd find often, probably the majority of the time, is that engineers would say, gosh, it's simply a value of ZG equal the complex conjugate of ZL. The conjugate match, that maximizes power flow. Everyone knows max power flow is maximized if we have a conjugate match. But it turns out the solution for that second equation is not to set the source impedance equal to the complex conjugate of the load. Instead, what we want to do is set that source impedance to be equal to the opposite of the reactance of the load, a purely imaginary reactance. Notice the real part of this is equal to zero. A very different answer than the solution to the first question. And when you think about it, this makes a lot of physical sense. If I want to set the source impedance such that the load impedance absorbs the most energy possible, I probably don't want to put any resistance in that source impedance. Resistance in the source impedance is just going to absorb some of the energy that could go to the load impedance, which in fact is what we're trying to maximize. If I want to go through and get the most amount of money to some person, I don't want to have a system where there is another person involved that spends that money. That's money that's gone and can't go to the person that I want the money to go to. So metaphorically, in this analogy, again, we replace money with power or energy. If I want all of the energy go to the load impedance, I don't want any way that source impedance can absorb energy. I want that source impedance to be purely imaginary. And in fact, that is the result that we get for that second equation. I'm sorry, I should have said the solution we get for the second question. Remember our first question. The first question was, what should the source impedance be? What should the load impedance be, rather, if we want to maximize the power absorbed by the load? The second question is, what should the source impedance be if we want to maximize the power absorbed by the load? In both cases, we want to maximize the power absorbed by the load, but in the two questions, we're either varying the load given a source impedance, or we're varying the source impedance given a load. And so it's no surprise that we should get different answers for those two questions, because the two questions are completely different. The two answers that we get are completely different as well. And make sure that you understand that. If you're skeptical, let's do the math and figure this out. Let's go through and see what happens when we make our source impedance equal to the opposite, purely reactive, the opposite of the load, and we make our source impedance equal to the complex conjugate of the load. If we go through and make our source impedance equal to minus JXL, we can calculate the power absorbed by the load, the power delivered by the source, and it's equal to this. Contrast that to the power absorbed by the load when we make our source impedance equal to the complex conjugate of a load. We go through the math, and what we find a result is that simply 1/4 of the result here. In the case where we set the source impedance equal to the complex conjugate of the load, we find that we have just 25% of the power absorbed when we use the optimal solution of source impedance. Now, this is all kind of very confusing. We went through and talked about available power, and this is the maximum power that the source can deliver. Yet, all of a sudden, we have a solution where the power absorbed is seems seemingly much larger than that. So, how do we put all these pieces together? So if we apply our optimal solution for given a load, what should the source be? We find that it will maximize the rate at which energy flows into the load. In other words, it'll maximize the value in terms of milliwatts, let's say. But it turns out that, of course, it will have a power which is less than the available power of the source. The load absorbs the available power of the source only when we have this conjugate match. ZL is equal to the complex conjugate of ZG. If we set ZG equal to the complex conjugate of ZL, then we have a conjugate match. And in that case, the power absorbed by the load will be equal to the power available to the source. If we set set the source to anything else, what we find is we don't have a conjugate match, and the power absorbed by the load will be less than the available power. Again, this is the quandary. We have a situation where this solution, we say, is optimal. It maximizes the power absorbed by the load, yet the result is one where the power absorbed by the load is less than the available power. In fact, it's far less than the available power. So again, how do we make sense of this? So for a fixed load, this source impedance, this reactive source impedance, we say will maximize the rate at which power is absorbed by the load. But now we're saying also that rate will be less than the available power of the source. Again, this seems to be contradictory. But here's the important fact. In the first question, we fixed the source and we altered the load impedance. As we changed the load impedance, of course, that didn't change the available power of the source at all. Remember, the source is fixed for that first equation. The available power is what the available power is, and it changes not at all as we alter the load impedance. But for the second equation, we fix the load and we change the source impedance. As we change the source impedance, we are altering the rate at which energy is flowing from the source to the load, but we are also changing the available power of the source. As we make our source impedance more and more reactive, less and less resistive, we find the rate of energy flow will increase. But we will also find that the available power of that source will increase as well, in fact, even faster. To see this, let's figure out what is the available power now of our source as we make the source impedance become this reactive value. If we do the math, it turns out the available power of that source is equal to infinity. The available power is the magnitude squared of VG minus 8 times RG, the real part of the source impedance. Yet the source impedance, in this case, has a real part, which is 0, since it's purely reactive. In other words, a source with a purely reactive source impedance has infinite available power. And that's why, of course, the power absorbed by the load is less than the available power, not because the available power absorbed by the load is somehow diminished or small. No, it's because the available power has exploded to infinity, and therefore any power absorbed by the load is going to be less than that infinite power. So this is really the crux of the controversy and why there is so much argument in electroengineering about this idea of maximum power transfer and should we have conjugate match or not. And it's a real argument. If you go through and look, Google conjugate match, there'll be people on both sides of the argument, particularly in the ham radio, amateur radio world. There's quite a bit of animus among designers with respect to this question. But the answer really depends on where you stand. And by that I mean where you stand on this equivalent circuit. Do you stand on the left side where the source is, or do you stand on the right side where the load is? From the standpoint of source, trying to figure out what the source should be, we say we want the source impedance to be, purely reactive. Well, what we're really saying is we want that source to have the largest available power we possibly can. If we're trying to get energy to flow down our system, we want our sources to have large available power. And that almost certainly means that the resistive component of the source impedance is as small as possible. On the left side, if you're on the load, what do you want to do? Well, the source is fixed. All you can do is try to coerce energy out of that source at the highest rate possible. And then your task is to make GZL, the load impedance, equal to the complex conjugate of the source impedance ZG. Now, the fact that you want your load impedance to be equal to the complex conjugate of ZG does not mean that the person on the right side, or left side rather, doing the source should make their source impedance the complex conjugate. No, they want to make their source impedance be as reactive as possible, as little resistance to up the available power. And that's, again, the argument. People that work on sources say, no, I'm going to make my source impedance have a resistance as small as possible, so I increase the available power. People on the other side, no, we want this conjugate match. The answer is we want both. We want to go through and take a source that increases the available power to as large a value as possible, and then we conjugate match to that large available source to be able to extract all of that available power. We always want to extract 100% of the available power of the source, but we also want that source to have the largest available power possible. The analogy then I always give is, if you like cookies and want to eat as many cookies as possible, there are two things that you need to do if you go to a party with cookies. First of all, you find the biggest plate of cookies you possibly can, and then you eat as many of them as you can. If you find a plate of cookies that doesn't have many, you can eat all of them and still be hungry. Ultimately, you're trying to get as many cookies as possible. And that's analogous, again, what we're trying to do in engineering here. We want our source to have the highest available power possible, and then we want to extract as much of that available power as we possibly can. That will cause the highest rate of energy flow along our system. And again, depending on where you stand on one side of that port plane or the other, you will come to different conclusions about what you should be. Now, one warning about all this, I talked about changing the source impedance. Remember, there's also a source voltage sitting there, which has been unchanged in that question too. That's a very academic question, really. We can't go through and simply change the source impedance while leaving VG to be unperturbed or unchanged. It's very difficult to do. Remember, VG and ZG are not physical elements. They're a model. Anything we do to the source will almost always change VG and ZG. So it's not that we're really trying to go through and make the source impedance more reactive and less resistive. What we really want is a situation to do something that maximizes the available power of our source as much as possible. The available power is really the thing that we're after when it comes to having a quality source with respect to power transfer. So to give some numbers, let's do a little thought experiment. And this is something that I actually saw more than once in my time as a working design engineer. So we go through and we look at a situation, and we're connecting a source and load, and we find that the load is absorbing energy at a rate of 200 milliwatts, 200 millijoules per second. And that 200 milliwatts is far less than the available power of that source. 500 milliwatts is the available power. And the reason we know that the available power is not going to be equal to delivered power is that ultimately we don't have a conjugate match. The load impedance is not equal to the complex conjugate of the source. The load impedance is not equal to the complex conjugate of the source. The solution that oftentimes engineers will prescribe is to sort of insert some resistance in the circuit to make the source impedance look more like the complex conjugate of load. We need this conjugate match to have maximum power transfer. If we can achieve that, we have maximum power transfer. So engineers will dutifully go through and achieve this conjugate match. What do they have? Well, now all the available power is absorbed by the load. We have now a situation where the available power is 100 milliwatts, and therefore it delivers all 100 of those milliwatts because we have a conjugate match. But have we really accomplished anything? In the previous case, we were absorbing energy at a rate of 200 milliwatts. Now that's only 40% of the available power. In our new design solution, where we've almost certainly inserted resistance, you always see this, increasing the resistance of the source impedance so that you have a conjugate match. All of a sudden, yes, we have a conjugate match. All of the available power is absorbed. All of the available power is delivered, but the delivered power is only 100 milliwatts. We only absorb energy at half of what we had before, the suboptimal solution where we did not have a conjugate match and therefore did not absorb all of the available power. And so again, which is the right answer here? One metric is what percentage of the available power did we absorb, but ultimately what we're really interested in is how much power are we absorbing or delivering in milliwatts, millijoules per second. Whether it's a large percentage of the available power or a small percentage of the available power, ultimately we're interested in how many milliwatts. And the analogy I use is if I were to offer you 1% of Bill Gates' net worth, just 1%, or 100% of my net worth, all of my net worth, which one should you choose? Well, I can assure you, you should choose Bill Gates' 1%. It's far more than my 100%. Find the biggest plate of cookies you possibly can and then eat as many of them as you can. Even if it's not all of the available, because the available is massive, still that will optimize or maximize the power, in this case, transfer, whether we're talking about cookies or dollars or milliwatts. So again, this is a really important concept in electrical engineering, this whole point of maximizing the power transfer. We really want to do that in terms of watts and not simply in terms of available power. Now, oftentimes to maximize that things in milliwatts, we do need to get 100% of the available power, but we don't want to sacrifice or reduce the available power of our source to achieve that equality of 100%. So the slide simply reiterates what I just got through talking about. In the second case, we get 100% of the available power, but it's only 100 milliwatts. In the first case, we have 40% of the available power, but that absorbed power is 200 milliwatts. And of course, that really ultimately is the better case. All right, it's better to have most of a lot rather than all of very little. So the bottom line here is be careful when we talk about maximum power transfer and conjugate match. And again, it's sort of a lazy statement that engineers make. Maximum power transfer occurs when we have a conjugate match. That is too simple a statement and too ambiguous to really do us much good. We have to go through and again speak more specifically about the problem. What is fixed? What is the variable? What are we trying to optimize? And depending on how we do that, we can get very different answers. And so we have to speak unambiguously in engineering so we get a precise answer that cannot be impeached. Again, electrical engineering, we find there's a lot of arguments that go on with respect to this conjugate match. If you're on the source side, you're saying, I'm trying to maximize my available power. And if you're on the load side, you say, no, I'm trying to extract that available power, all available power from that source. Even though the equations of each seem to be different and contradictory, they're not contradictory. Both of them are correct with respect to which they stand. One tries to make the cookie as big as possible, the plate of cookies as big as possible, and then the other one tries to eat as many cookies as possible. Make the available power as big as you can, and then try to extract all of that available power if ultimately that's you're trying to maximize the power absorbed by that load.